Number Theory Section 4, Diophantine Equations. Video 3, Pell's Equation. Pell's equation is the name given to the equation x squared minus ny squared equals 1, where x, y and n are positive integers. Let's start by looking at how we could write a program to solve equations of this kind. I'm going to start by defining a function which I'm going to call Pell, and I'm going to input n and also a variable called max, which is how far I want my program to search for solutions. And then for I in the range from 1 up to max plus 1, and for j in the range from 1 up to max plus 1, I'm going to look for solutions. So if I times I minus n times j, so that's my x squared minus ny squared, if that gives me a value of 1, then I've found a solution in my range. So I want to print I and j. Now notice that I and j both go in the range from 1 to our maximum, rather than I going from 1 and j starting from I. That's because, once again, we're in a situation which is not symmetrical. Now, once we've got a program that we can use to solve Pell's equation, there's a really neat trick you can do to find further solutions once you know a particular solution. And that's using this difference of two squares method, where we write something as x plus the square root of n times y multiplied by x minus the square root of n times y equals 1, and then raising both sides to a power. So let's look at an example to see how this works. Use a program to solve x squared minus 3y squared equals 1, where x and y are both less than 100. Use your largest solution to generate a further solution. So going back to my program, I want to solve x squared minus 3y squared equals 1. So I'm doing Pell's equation where n is equal to 3, and I want solutions up to 100. So I'm going to put in my max equals 100. And so that's given me some solutions. I can check this smaller solution. So 2 squared minus 1 squared times 3, so that's 4 minus 3 is 1. 7 squared is 49. Take away 3 lots of 4 squared, so that's 3 16ths, which is 48. So 49 take away 48 would give me 1. So yes, it looks like my program's doing what it should. Now the largest solution that I got, less than 100, was x equals 97 and y equals 56. So we're going to use that to generate a further solution. So x equals 97, y equals 56 is a solution of x squared minus 3y squared equals 1. Now, I'm going to use this strange difference of two squares trick. So I know that if I've got x squared minus 3y squared, I can rewrite that. So 97 plus 56 root 3, 97 minus 56 root 3 equals 1. And I know that that's true because this is the difference of two squares. That's giving me 97 squared minus 56 squared times 3. Now I'm going to raise both sides of this equation to the power of 2. So I'm going to square this, and then 1 squared is just 1. So I've still got something with 1 on the right hand side. So working all of this out, well, when I expand these brackets, I'm going to get a whole number term from squaring that. I'm going to get a whole number term from squaring that, and then my cross term will be 2 times 97 times 56 times root 3. So I'm going to end up with something of the form a plus b root 3. And in fact, what I will get is 18,817 plus 10,864 root 3. And similarly, when I do the other bracket, I'll get the same number again, 18,817, but this time minus 10,864 root 3. And then that is equal to 1. But this is just a plus b, a minus b again, which means that it can rearrange to give a squared minus b squared. So I will get 18817 squared minus 3 times 10864 squared equals 1. So that means that x is 18817 and y equals 10864 is also a solution. So I used a fairly small solution, 97 and 56, to find a much bigger solution. And I could do this over and over again and keep on generating new solutions from my old ones. Let's see that written out neatly. So in my first line, I used the difference of two squares to rewrite x squared minus 3y squared as 97 plus 56 root 3, 97 minus 56 root 3. Then I squared both sides and then expanded and simplified to get it in the form 18817 plus root 3 times 10864 and 18817 minus root 3 times 10864. And then because this is again the difference of two squares in the same format as I had before, that this is also a solution. We can use this as a way of approximating the square root of n, because we can rearrange Pell's equation as follows. So instead of x squared minus ny squared equals 1, I can rearrange it to get x squared minus 1 over y squared square rooted equals the square root of n. So that means that for any given solution, x over y is an approximation to the square root of n. And the larger the x and y are, the better the approximation will be. So that means that since x equals 18,817 and y equals 10,864 is a solution to x squared minus 3y squared equals 1, I can find an approximation to the square root of 3 by working out 18817 divided by 10864. So if I work out the square root of 3 first of all, you can see I get 1.73205 and some more decimal places after that. If I work out 18817 divided by 10864, you can see how closely these two match. So all the way up to here, up to the 1, 2, 3, 4, 5, 6, 7, 8th decimal place, these two would be the same. In this video, you've learned the classic form of Pell's equation, how to generate solutions of Pell's equation from another solution, and how to approximate square roots using solutions to Pell's equation.